Hi guys, it's Miss H, and this is our last video on energy. This video is going to be about kinetic and potential energy. So if you recall, kinetic energy is the energy of moving things. So the faster that something is moving, the more kinetic energy that it has. The variable that we use to represent kinetic energy is a capital K, capital E, but you will also sometimes see it represented with E, a capital E with a subscripted K, just depending on what kind of reference table you're looking at, but our reference table uses capital K, capital E. The unit for any form of energy is always going to be joules, and the formula for kinetic energy is 1/2 mv squared. But when I type that into the calculator, I'm going to type that in as 0.5 times m times v times v, and the reason I do that is because the calculator is less likely to make a mistake that way, because depending on the kind of calculator you're using, if you hit that square key last, it might try to square everything instead of just the v. So if you're using a graphing calculator, it's probably going to be okay to do it the regular way, but this is the way that I prefer to do it just to make sure. We can still put this formula into a triangle, but we're going to have to modify our triangle just a little bit now to make it so that it can actually fit all of the stuff in here. So KE goes in the top because this is all multiplied together. We need to keep it multiplied together in the bottom. 1/2 m and v squared go in the three sections in the bottom. So obviously 1/2 is a constant. I'm never going to be solving for that. But if I'm solving for m, I'm going to have KE over 1/2 v squared. And if I'm solving for v, I'm going to have the square root of KE over 1/2 m. So now let's take a look at some example problems. Number 1, what is the kinetic energy of a 65 kilogram skier moving at 7 meters per second? So we're going to start with identifying. So kinetic energy is what we are solving for, so that's KE. 65 kilograms, that's a mass, and 7 meters per second, that's a velocity. So step 2, we write the formula, KE equals 1/2 mv squared. Step 3, we're going to plug in our numbers. So KE equals 0.5 times 65 kilograms times 7 meters per second times 7 meters per second, which you might know is actually 49. So then KE, when I type all of that into the calculator, gives me 1,593 joules. So 1,593 joules of kinetic energy. Example number 2. What is the mass of an ice skater that has 625 joules of kinetic energy when traveling at 5 meters per second? So we're solving for mass. We're given 625 joules of kinetic energy and a velocity of 5 meters per second. So if I look back at my triangle, I see that mass equals kinetic energy over 1/2 velocity squared. So when I plug in my numbers, that's going to be 625 joules on the top, 0.5 times 5 meters per second times 5 meters per second, or 0.5 times 25 meters squared per second squared. So that's going to be 625 divided by 12.5, and so that gives me a mass of 50 kilograms. So 50 kilogram mass for this ice skater with 625 joules of kinetic energy moving at 5 meters per second. Our third example, how fast is a 3 kilogram ball rolling if it has 37.5 joules of kinetic energy? So how fast means that I'm solving for velocity. 3 kilograms is my mass, 37.5 joules is my kinetic energy. I look at my triangle, V is the square root of KE over 1/2 m. So that's going to be the square root of 37.5 joules over 0.5 times 3 kilograms, or the square root of 37.5 joules over 1.5, or the square root of 25. And so V equals 5 meters per second. Okay, so 5 meters per second is the velocity. So next we're going to move on to potential energy. So recall that potential energy is energy that is stored. If it is stored due to shape, we call that elastic potential energy, that is compression and expansion. We're not going to be dealing with that on this PowerPoint really. That was in the first one. So the more stretched or compressed, the greater the energy is. The energy stored due to position is called gravitational potential energy, and the higher that the object is, the more gravitational potential energy that it has. The variable is PE, or PE with a subscripted E for elastic, PE with a subscripted G for gravitational. Again, you might sometimes also see a capital E with a subscripted G for gravitational potential energy, or a capital E with a subscripted E for elastic potential energy. But again, we're gonna stick with what we're gonna see on our reference table, and what you're gonna see on your reference table is this guy right here, the P, capital E, capital P, capital E with a subscripted G for gravity, acceleration due to gravity. Again, the variable for all forms of energy is joules. And so our formula is PE equals mgh, and I'm usually just going to say PE instead of PE subscript G just because that's a little faster to say. So our PE goes in the top, M, G, and H go in the bottom. So again, your mg and h are multiplied, so you have to keep those together in the bottom. Let's take a look at some examples. So example number 1, how much gravitational potential energy does a 4 kilogram cat have while sitting on a shelf that is 2 meters high? So 4 kilograms is my mass, 2 meters is my height. I'm asked to solve for gravitational potential energy, and we can assume that this cat is on Earth. So we can assume that G is going to be acceleration due to gravity on Earth of 9.8 meters per second squared. So step 2, we write our formula, PE equals mgh. So that is going to be equal to 4 kilograms times 9.8 meters per second squared times 2 meters. And so that gives us a total amount of energy, or a PE, gravitational potential energy of 78.4 joules. 78.4 joules of gravitational potential energy for this cat. Example number 2, what is the mass of a box that has 60 joules of potential energy when it is sitting on a table that is 0.5 meters tall? So we're solving for mass. We know that we have a potential energy of 60 and we have a height of 0.5. And again, we can assume that we are on Earth. So G is going to be 9.8 meters per second squared. If we look at our triangle, we know that M is equal to PE over GH. And so we can say that that is going to be 60 joules divided by 9.8 meters per second squared times 0.5 meters. And so if we plug that into the calculator, we get an M of 12.2 kilograms, 12.2 kilograms of mass. Our final example is going to be looking for how far. So how far above the ground is a 0.5 kilogram bird with 20 joules of potential energy. So how far is height? The mass, how far we're solving for height. The mass of the bird is 0.5 kilograms and the gravitational potential energy is 20. Again, we're going to assume that this bird is on Earth. So G is going to equal 9.8 meters per second squared. When we plug this into our formula, or when we look at our triangle rather, we have H equals PE over mg. Remember that mg is also another way of solving for a weight, so that could also, you could substitute in the weight there if that had been given to you instead. So that's going to be 20 joules over 0.5 kilograms times 9.8 meters per second squared. And when we plug that into the calculator, we get a height of 4.1 meters. So this bird is 4.1 meters above the ground. You could also potentially be asked to solve for G, but if you're asked to solve for G, you'd have to be told that you are not on Earth. So you'd have to be told that you're on the moon or Mars or some other planet or outer space or someplace else in order to be able to solve for G. Otherwise, you will assume 9.8 for G unless you are explicitly told that you are somewhere else and you need to use a different G, or you are asked to solve for it because you are somewhere that is not on Earth. The last thing we want to look at is the conservation of energy again. So remember that the conservation of energy says that energy can't be created or destroyed, it changes forms. So we have this energy conversion that goes back and forth between gravitational potential energy and kinetic energy as an object falls. So as an object falls, it trades off decreasing gravitational potential energy because it's getting lower for increasing kinetic energy because it's speeding up until it hits its terminal velocity. So because of this, we can set the two formulas equal to each other. So we can say that KE equals PE, or 1/2 mv squared is equal to mgh. And so that actually will allow us to solve for other variables that are in there that we aren't given the other way around. So if we take a look at an example of this, a 1.2 kilogram rock is dropped from a height of 2.5 meters, assuming that 100% of the original gravitational potential energy is converted to kinetic energy, and also assuming that it doesn't hit terminal velocity before that happens. How fast was the rock traveling the instant before it struck the ground? So because we can set these two formulas equal to each other, the instant before the rock strikes the ground, it should have its maximum velocity if it hasn't hit terminal velocity, and that 100% of that gravitational potential energy should have been converted to kinetic energy the instant right before it strikes the ground. So our mass is 1.2, our height is 0.5, and we're asked to solve for velocity. So we're going to start out by setting these two formulas equal to each other. So mgh equals 1/2 mv squared. So I have 1.2 kilograms times 9.8 meters per second squared times 2.5 meters is going to be equal to 0.5 times 1.2 kilograms times v squared. And v is what I'm solving for. So if I plug all of this into the calculator, I end up with v equals the square root of 49 meters squared per second squared once I type all that in. So my v is equal to 7 meters per second. Okay, so 1.2 times 9.8 times 2.5 gives me 29.4. 1/2 times 1.2 gives me 0.6. 29.4 divided by 0.6 gives me 49, and the square root of 49 is 7. So that kind of gives us an overview of kinetic and potential energy formulas, how to solve for them, and also being able to set them equal to each other.